to where you ended up, right? If they go directly to that location, how fast should they drive? That's what it's telling you, the V total. Well, the problem will give us, is telling us that if the person drives 29 miles an hour, which is a street speeds, right? You can go 100 miles an hour, 84 miles an hour. The other car can go 29 miles an hour and catch up to you right there. And so the direction, the theta, is the direction that they have to go at to catch up to you. So the direction, the 63 degrees that we got, is this angle right here. $63 degrees, you see, right here. So the person, if they want to go in a direct line path, should go 29 miles an hour at an angle of 63 degrees north of what? North of west. So that's the answer here. Okay, north of west. Okay, now we will answer the last question, which was find the average acceleration. Average acceleration in stage 1. Now, in this problem, I'm going to assume, just to make it a little more simple here, I'm going to assume that the car already was moving here, and then at the end here, it just basically turns around. So assume that it doesn't really come to stop. It just turns around, then the third path, it goes like that too. So the average acceleration in each stage is going to be 0. The car's going to start with the same velocity, end with the same velocity. So average acceleration in the first stage is going to be 0. Average acceleration in the second stage is going to be 0. So there's going to be no average acceleration in each particular stage. So the model that I'm basing this on is as if, think about it as almost like a billiard ball is moving like this. It's just going. And then we start doing the analysis of the problem once the billiard ball reaches this location right here. So the billiard ball was already moving. And then let's just say this is the XY axis. So we start analyzing what's going to happen to the billiard ball right after it crosses the origin. So the ball is already going, and at this location something happens to it that makes it change direction, and now the billiard ball goes this way. Right? And then at that point, what happens to it, we don't care. After that point, we're not analyzing the problem after that point. So that's why in each particular stage, there are no forces applied on the ball, so the average acceleration is 0. So the meaning of the average acceleration, A average is F average divided by M, right? Newton's law is F equals ma. So by asking average acceleration, what is the average acceleration? I'm actually asking what is the average force on this car, or what is the average force on the ball, you know? So if the ball is just already going and over here it just turns around, the average acceleration along this stage is 0, along that stage is 0. The only thing that is happening is there is an average total acceleration, and most of it is taking place right there at the corner, you know. So it's equal to V average 2 minus V average 1 over T total. This will give us the average acceleration over the whole stage. It will not give us the instantaneous acceleration at the corner. That one is bigger in magnitude. Okay, so V average 2 over minus V average 1 over T total, right? So what we do is now we can take that, you see V2, that is the average velocity in the second stage. This is the initial velocity at the first stage. We can subtract these, this minus this. So let me just write it like this now. 84 at 20 south of east minus 100 at 40 degrees north of west divided by the total time. 61 over 60. Now, what do I expect to get? What kind of vector do I expect to get? I can make a little prediction here. I expect to get a certain vector that looks like this. Something that is pointing in this direction. As a matter of fact, that could be a way of you testing your answer to see if you're right. I expect the average acceleration vector to be in between the average v vector 1 and the average v vector 2. Right? This is the average v vector 1, this is the average v vector 2. I expect the average a vector to be in between. Why do I say that? Why do I expect that? You probably already know the answer, but maybe you can't put it in words, right? If something is going this direction, and then if that thing turns the direction, something must have hit it this way, right? Somebody must have hit it this way, you know, to cause it to change direction. Could that person have hit it this way? No. If it goes this way to this way, whoever hit it must have hit it between these two vectors, right? They can't have hit it this way. If they had hit it this way, let's use this one. If they had hit it this way, then it would have turned something like that. The ball would have gone this way. So you see, whatever you hit it at is always in the middle between the direction that the ball is going, that the ball changed direction, you know. So I expect the average acceleration vector to be in between. So we can use that fact later when we get the answer to check our answer, okay? So let's see here. How are we going to do this? Well, in order to actually subtract these, we got to break this up into a vector, break this up as a vector into I and j component, and then subtract them, right? So A average total is going to be, break up 84, right? 84 south of east. So that's going to be this one here, 84. This is the V2 vector. So 84 cosine of 20, right? I hat. That's the x component of V2. And then the y component of V2 is negative. See, it's going like that, going like this. The y component of dV2 is negative 84 sine of 20 j hat. So that's the V2 vector. And then we subtract from that the V1 vector, which is 100. Let's see, the x component is negative here. Negative 100 cos 20. Negative 100 cos 40, I meant. I hat. Plus (100 sine 40) j hat. Okay, so we got to do this minus this over the total time, which is 61 over 60. So A average total is going to be